So for the last talk of our beautiful conference, we have Reiko Toriumi for Hoist, who's going to talk about renormalization of enhanced quartic tensor field theory. And please, Reiko.
Okay, thanks. So I'll tell you about this, I'd say rather exotic phi-4 field theories, and where phi is now tensors. And we have, it's a joint work with Joseph Benjelloun. So I'll show you what I want to tell you about. So tensor field theories, it's been, I guess, introduced also by Leonard and Joseph and a little bit Dario. And so I can give you it this way. So it's a field theory of order D tensors. So order D, so D, little d is a number of indices of tensors. And these tensor fields, they map group G to the D. To, in this case, I write you complex, but you could, in principle, have real or anything else as you wish. And the group can be anything as you wish as well, in principle. And you may have a kinetic term. Mu here is a mass. And then you may have other type of quadratic terms. Quadratic terms. And the kernel is denoted by K here. And then you may have interactions. So you could have many, and in fact, you could even have infinitely many of them. I denote it by big B because we sometimes call them interaction bubbles. And it comes also with, each of them comes with coupling constant lambda. And here you could have as many phi's and phi bars as you wish. And I give you the kind of representation, graphical representation of how the tensor indices are contracted. So what is interesting for the tensor case is that you may have, so if you go to order 3 tensors, you may have, if you consider 5, 6 interaction bubbles, you may even have 3 such possibilities, etc. Okay. So then, also because we're dealing with Gaussian kinetic terms, you can do Wick contraction, and then you generate, your theory will generate Feynman graphs, and they are D+1 edge-colored graphs. Okay, and then there is this theorem that says D+1 edge-colored graphs are due to a simplicial triangulation of piecewise linear d-dimensional pseudo-manifolds. So with this, and also, let's say, inspired by matrix models, which successfully describes 2-dimensional quantum gravity, one can just say, you know, at least a priori and naively, you can say that this kind of tensor models, or tensor field theories, for example, should be relevant for addressing the problems of quantum gravity in dimensions higher than 3, let's say. Okay. So if you want to talk about tensor models, you can say that this is a statistical version of tensor field theories. So there's no more propagating degrees of freedom. Propagators are basically trivial, and you may just have, instead of groups, you may have just indices. So these take integer values. And then, so mentioned earlier a little bit, but so tensor models exhibit large n expansions. And in the large n limit, there is this parameter called growth degree, which was mentioned before, which is analog of, let's say, genus in matrix models. But growth degree is not a topological invariant, but it's not a topological invariant, but still combinatorial invariant. And when this growth degree is 0, just like a genus is 0 case, this class of graphs are called melons, and they are subclass of spheres. So there are more spheres than growth degree being 0. But okay, so in this large n limit, melons dominate. So these are basically melonic graphs. I can show. And they are shown to be branched polymers. So they are trees, basically. And in the sense of, in the context of quantum gravity, we want something that's not really branched polymer. Branched polymers are like trees, and they're a bit, in the large scale, we want something more connected and kind of large for a universe. So from quantum gravity point of view, we want something more than, we don't really want branched polymers. We want to get away from it. So one of the such proposals is given by Valentin Bonzon and also Vincent Rivasso. And the program is called Enhanced Tensor Models. So there they introduced a non-melonic interaction, in this case something called necklace, and then you scale it in a proper way in N so that they can compete with melonic graphs. Okay. And encouragingly, what they were able to do, can you hear? I don't know. Able to do is they were able to achieve actually 2D quantum gravity, and also actually you can tune these things, and you can also achieve also branched polymers, but also in between something called baby universes. But the point is, anyway, with this enhanced program, you can actually get away from branched polymers. So inspired by that, but that is in the statistical model setting. But we were interested in doing it in field theory setting, where the renormalization group method is readily available, and of course now you have the propagators, so dynamics and geometry can possibly change. So we wanted to see that. So we consider, again, so this is a little bit of repetition, but so in our case, our group is, we just take it to be U1 to the power of big D, actually, D copies of U1. And then we have order D tensors again. And tensors are now, it takes the values, complex values. And then we're going to work in a momentum space. Okay, that's our preferred space. And again, action is given by that. And again, we have a mass term, and then the kinetic term is there with the kernel K. And in our case, we can take rather simple kinetic term. So the power of momenta is given by 2b. Okay. And remark here is that, so a priori, so we are not, so we are working, we are studying field theory of geometry rather than field theory on geometry. Geometry referring to, say, let's say RD or something, or our space-time. So there is no restriction on the value of B coming, for example, coming from Osterwalder-Schroeder positivity axiom a priori. We don't really care about this. But then we take it at least to restrict B to be a positive real number, at least in our model. Okay, so our enhanced models, is spanned by these 4 parameters, where, sorry. Yeah, so the big D is this D copies of U1, and then the little d is the order of tensors, and then A is, as you can see, it's associated with the enhanced interactions, and then B is basically power of propagator. Okay, so we consider 2 models. I'm going to talk mainly about the model plus. So if you want, you can forget about model times. but so basically, I have 2 different kinds of 5-4 interactions. And this is rather traditional one. And this one, which comes with the coupling lambda. And then the other one, this is the enhanced one. And enhanced with extra powers of momenta, basically. And then it comes with the coupling lambda plus. And then I have the mass term, and then also normal kinetic propagator. And this term is there so that the model can be renormalizable. And then similarly, I have another type of model, which is enhanced. This one is, I guess, kind of doubly enhanced. But yeah, I'll show you. So let me just, I'll show you what it looks like a little bit more graphically. Maybe you can view it a bit better. So this is the model times, which I won't probably talk about so much, but okay. So so I have the normal, rather 5-4 interaction. This is bubble. This is actually a melonic one. And another one which we enhance. So on this side, sorry, this is something called colored representation, and this is a stranded notation. I put both sorry, for people who prefer either way. But basically what happens is that we enhance these bold fat edges or these strands so that they have more momenta. They come with more kind of powers of momenta. And you can denote the other terms in this way. But you can think, so there was a talk of Yang-Mills earlier, but also some QCD, etc. There you also have kind of a derivative interaction term. So you can kind of think of these enhancement of extra powers of momenta as kind of like a derivative. You can think of it that way. And whereas for enhanced model plus, instead of enhancing both sides, we only enhance one of them. Okay. So traditionally, both are actually melons, but I kind of fatten on this side. So we will see maybe possibly we'll see effect of kind of making it a little bit not so melonic. Okay. So this is the model plus. And for example, as advertised, so this is these graphs are for order 3 case for illustration. But on the left-hand side, I have a melonic Feynman graph. And then on the right-hand side, I have a non-melonic Feynman graph. And if you indeed compute amplitudes of these for a given set of parameters, that I had 4 of them, then actually the non-melonic one dominates, or they are more divergent. So indeed, you can actually make them more dominant. So the amplitudes of these graphs are as kind of same as standard QFT, is given by the product of propagators, which is denoted by C, and then the products of the vertex weights, which contains the coupling constants. And then if it's enhanced, then there comes with more momenta weight. And you can achieve these omegas are superficial degrees of divergence, and you can achieve how they look like. I won't explain too much about what they mean, but you can achieve. And so this is we are getting to the power counting theorem. So we have a list of primitively divergent graphs. So primitively divergent graphs are the ones that don't have any subgraphs which are divergent. And so the first, so let's say, so there are different kinds of graphs, but nx is the number of external legs. And so I have 4-point function, and then I have the rest are 2-point functions. Okay. And then the V2 is a number of this kind of interaction bubbles in your graph. And V2A is a number of the kind of interaction bubbles, and V4 is the more traditional 5-4 one, and then V plus 4 is the one that's enhanced 5-4 interactions. And rho plus is the number of enhanced 5-4 interaction bubbles, which have edges that go through internal faces where we sum over momenta. Okay. So omega is a superficial degrees of divergence. So these are either logarithmic divergent or divergent in D over 2. Okay. So for example, maybe if I look at the class 2, these guys would renormalize 2-point coupling ZA. As you can see, so this one it's missing one of the enhanced ones, which means that one of the enhanced edges, they will go through the external legs. So therefore, maybe it's basically renormalizes ZA. Well, it's a bit maybe hard to understand what's happening. Okay.
Why did you choose the values of A and B?
Sorry, I didn't. Okay, so maybe I should say, so because those are the ones that gives us just renormalizable model. Sorry, yeah, sorry, yeah, maybe I should skip the order. I'm sorry. Yeah, so thank you for the question. And this is not that important, but I wanted to show you what kind of values they take. So so this is a order 3 tensors and this order 4. Of course, they don't stop here. You can go anywhere as you wish. And this is the dimension of the group. And most of the time, A and B, they don't take integer values in this model. Okay. And so this is, so you can forget about it if you want, but this is model times the other model. And, but maybe, Did I do something? Okay, thanks. Thank you. But what you can maybe notice is that this also maybe, so yeah, you tell me your opinions later, but 4 point, you see that there is no divergent graphs for 4-point functions and only 2 points, so mass or kinetic term. So yeah, so, but I'll maybe visit this after talking about model plus, if I had the time. Okay, so going back to model plus, I want to show you what kind of primitively divergent graphs I have in a more graphical manner to all orders. So to prepare the ground for that, I just want to point out that so if you insert this kind of enhanced melonic graph, then in a particular way, has to be in a particular way, but then it doesn't change the superficial degree of divergence. Whereas if you insert this kind of what we sometimes call a dipole enhanced one in a particular way, it reduces the superficial degree of divergence by d/2. Okay. So with that in mind, so if you look at the 4-point divergent graphs, which renormalizes 4-point coupling lambda, then I have these kind of graphs. So this is the one loop order, and then you insert the enhanced 5-4 coupling, and then you won't change the degree of divergence, and you can insert in this kind of way, and there are infinite number of family of them, okay, as we wish for the just renormalizable models. And their boundary graph, I just wanted to, all of them, they have the boundary graph like this. That's why they will renormalize 5-4 coupling lambda, simple lambda. Okay, yes?
Number of primitively divergent 4-point graphs infinite?
Yes.
And for the 2-point?
Also.
It's also infinite?
Yes. 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 I'll show you the next slide. So this is the ones that renormalizes the mass. And so I don't know if you can see, but I put, so this is not the end. I just show you some illustrations. So there's more, there's many more. So this is the one loop one, and then you can insert the enhanced melonic one in this manner and that manner. So this is a stranded notation, and that's the color notation. They're the same. And so all of them actually, they have a superficial degree of divergence d/2. And this was actually corresponding to the class 2 in the table that I showed you earlier, class 1. But you can insert also the enhanced d dipole, and then it will reduce superficial degree of divergence by d/2, so it becomes log divergent. But I didn't show you what they look like, but you can insert them in actually dotted where the propagators are, actually. So it's infinite family of them. Sorry.
We can understand completely the combinatoric of all primitive graphs.
Not yet, so that's it. Sorry, this is a preview to the maybe next problem. Yes, yeah, but exactly. And then there's another one that renormalizes mass. The mass, it's a similar way. Okay, and then there's another 2-point coupling. And as you can see, that all of this, the boundary graphs are the one on the top, and this comes with a ZA coupling, and it's exactly basically the same. All of them have superficial degree of divergence d/2, but you can insert the enhanced d typo, and you can get logarithmic divergence ones. Okay. So anyway, so this is a rather standard, procedure, but maybe I'll flash just so that we are on the same stage. So we're gonna try to do a renormalization group analysis with Wilsonian renormalization approach using multiscale analysis. So multiscale analysis, I give you here the covariance propagators in Schwinger parameterization. And so what we are doing with the multiscale analysis is that we are slicing up the propagators so that propagators become sensitive to the scale. And this way you can do subtract precisely counter terms and etc. You can do good renormalization group analysis. So big M is just a constant. Little I is the one that's the scale, basically. And just as a comment, so for physicists, for UV, it's correspond to big I scale, and for that corresponds to small alpha, the Schwinger parameter. Okay, then we're gonna integrate the fields at high scales. Here, and then so we're gonna take Wilsonian approach. So we're gonna integrate out another little layer down to scale I-1. And because we're dealing with Gaussian fields, we can decompose the propagator readily and also the fields, and then we get another effective action. And the effective action is written there, but if the theory is renormalizable, then it should take the same form as the original action. So I should have the quadratic term and the quartic term, and the remainder is denoted as R, which is just finite terms, so which they don't matter. Okay. So now take the 2-point function, and I'm going to Taylor expand because I'm doing perturbation theory. So studying the table that I showed you the list of primitively divergent graphs earlier, you can conclude that this one, sigma evaluated at the moment, external moment of 0, this is divergent with this class 1 and class 3 gives you d/2, and class 4 and 6 gives you log divergence. But d/2 is actually smaller than 2b, so this term is actually not there, in fact. And then this one is divergent, again dictated by the classes of class 2 and 5. And the rest are actually finite. So this all comes from already the table that I showed you, actually. And then you can do a similar thing for the 4-point function. And again, this one is the divergent one. It was the first row with logarithmic divergent one. And then this one is actually, we'll renormalize the enhanced one, but indeed it only had the leading order term. So the one that has the coupling of interaction of itself, and that was the only divergent one indeed. And then not the side divergent, sorry, yeah. And then the rest is actually finite. Okay. So then, sorry, I'm continuing with effective action analysis, but you can, this standard, so you don't have to, you can just listen and go away, but You can identify the renormalized mass in this format. And also actually wave function renormalization is given this way. I keep writing, so I can show the pink one, but it's actually 0 in our case, meaning the wave function renormalization is absent. It's just simply trivial and 1. And then I'll keep going. So effective theory can be written. I can massage it a little bit, and then I'll do a field rescaling. But then again, as I said, we actually don't have any wave function renormalization. It's 1. So, but still, I write it explicitly, and you can identify all these couplings, which were in our original action also. So, but then as I said, so if I make wave function renormalization 1, then I achieve this relationship, basically renormalization group equation. So for the analysis, for following analysis, we're gonna set actually big D to be 1 for simplicity, but you can do it for also not necessarily 1 case. So if you look at the 4-point coupling lambda, up to 1 loop, you have this graph, original 1, and then the other one, 1 loop 1 that we already saw earlier. And so here I give you, so this is basically already flow equation for lambda and also for lambda plus. And observations already before I keep going. Lambda plus does not run. And another thing that one may want to note is that I can never set lambda and lambda plus to be the same because these equations, they will be not consistent with each other. And also another thing is because S0 is positive, it's the renormalized coupling is smaller than the lambda UV1 and a bare one. And then it seems that lambda increases in the UV, but it's not going to be an ordinary lambda ghost. We will see later.
Your statement that lambda is it treated to all orders, or you just
yes. It's a good point, but yes, it's I'll state to all orders, but it's so at the moment I'm only computing after 1 loop, but even from the list of the table you can already analyze it. Maybe should I go back? Yeah. Oh yeah, so that was sorry, I didn't realize how far I have to go. You can already see these are the all primitive divergent graphs, and only 4.1 was the one that, so it basically, this one uses up all the enhanced ones, which means, and also there is nothing of this sort, which means that there is nobody who is divergent that renormalizes lambda plus, which had the external enhancement. So yes, it's to all orders actually. Okay, sorry, these are some comments up to here, but one can indeed evaluate this as S0I. Maybe it's not that, maybe I shouldn't go into too much detail, but so let's consider this quantity. And since, since I'm in the UV right now, and from high scale, I'm integrating over little by little. Alpha is small, so I can Taylor expand this exponential to the alpha term. And then I'm going to use also something called Euler-Maclaurin formula, which essentially that you can rewrite the discrete sum into integral with some remainder, and then you can actually evaluate it. Okay, and this is the results. So m is again, it's just a constant, which is bigger than 1, but it's a constant. And so this is actually positive quantity. Okay. But what I skipped a little bit was that actually alpha, for example, if you go back to the Stringer parameterization representation of the propagator, you notice because alpha and the momenta p to be, they're sitting in the exponential argument of exponential, you notice that alpha should have a dimension of -2b in units of momentum scale. Okay, so you have to take care of that. And then Q is also momenta, so you have to take care of the fact that it actually has dimension in momenta. So if you take care of this change in variables, and then, but then in this case, for 4-point function, it's actually, so still this quantity was actually dimensionless, just happened to be. So it's still the same. Okay, so finally, then I introduce a log of momentum scale, which we denote by T, which corresponds to I log M in the multiscale analysis. Then I achieve at the flow equation for lambda in terms of T. And then we can integrate the both sides. And then you can indeed reach to this equation for lambda. And let's just look at it a little bit. So observation is that indeed there is no pole in the solution, so there is no lambda ghost. And at large T, so at UV scale, and if lambda plus, the enhanced one, is non-vanishing, so the enhanced coupling is there, then lambda T is bigger than lambda T naught, where T naught is some IR scale, reference scale. So the bare coupling, you'd assume it's not vanishing. So then the model doesn't seem to be asymptotically free, and maybe it is possibly asymptotically safe model, but in that case, yeah, we do need to compute all orders or do some non-perturbative results. And also, just to say, if I set lambda plus to be 0, then lambda can be a constant. But then, of course, this means that enhancement disappears, and yeah, the model goes back to normal tensor field theory, except that now the dominant graphs are not melonic. So, but yeah, so but this model, this doesn't seem to be very interesting either. Anyway, sorry. So, and then we can do a similar thing for 2-point function, ZA, 2-point coupling ZA. And then you again have to take care of the dimension for quantities. And also note in the lambda plus doesn't run. You can again integrate both sides of the flow equation, and this is what it looks like. So observation again is that ZA decreases exponentially in the UV, and then well, it reaches to the second term at some point. And then in the IR, ZA also again blows up. Okay. And again, so sorry, so you can do for the mass as well in a similar way. And so what I should say here is that we say that mass scaling dimension should be determined by the maximal degrees of divergence of the 2-point amplitudes. So we say that mass should be in dimension 1/2 in momentum scale. And then you take care of the dimensional dimensionfulness. And then you achieve that again, the beta function from the mass. And you can also integrate it both sides. And in the UV, exponential term basically goes to 0. And so the second linear term dominates, which is, so it goes like this. And beta is actually a positive quantity. So it means that mass becomes negative. And also it seems to grow linearly with T. And that seems, I guess, at least straight to us. But in the IR, exponential term dominates. Okay, so this is summary, but maybe, I don't know if unless you want to stare at it, I may keep going. And of course, there are already questions on this, but okay, you can go higher in order. This is just one higher order. You can compute if you want, but we can actually do better without even we haven't done the actual analysis, but you can go to all orders. You can guess what they look like. Again, there was already a question from David, but lambda plus is constant at all orders. And for lambda, this P is given by, these are all coming from the list of all these primitively divergent graphs. But you can say that it should be in this form where P is a polynomial in lambda plus. Okay. And then also mass, all these R's are polynomials in lambda plus, and they should take this kind of form. Okay, we don't know what these polynomials look like yet. And then Z is the same way. And indeed, especially for Z, how it behaves in UV and IR depends on the signs of this polynomial Q. Okay, so that's left for the future work, possibly. And maybe I'll talk a little bit about model X. I'll flash some slides. Sorry, so they look like this, but basically, sorry. So in this case, I'm sorry, I didn't mean to. So in this case, as you can see, this one, they contribute to the mass renormalization. It's log divergent. So the mass doesn't have, mass doesn't have a scaling dimension in this model. And let's see. So let me just go all the way. So this is a summary. So left-hand side is the differential equation, and then the right-hand side you integrate. So again, in this model, both phi4 couplings, enhanced or not enhanced, they're actually constant. And then only I have renormalization for 2-point functions. And actually, they all grow linearly in T, and also negative actually. Okay, so also you can do to all orders again, but the behavior stays the same basically as one loop case. So it stays constant, and also these are PQRs are just polynomials again, but they grow linearly in T in this magnitude. Okay, so conclusions. So these models maybe kind of exotic phi4 models. I don't know if it's interesting or not. If you have some comments, we are very happy to hear about it. But from the quantum gravity point of view, I think maybe you already saw, probably many of you saw, but to me it looks like actually again trees. And that's precisely why probably we already know what kind of that we can probably resum it to all orders and can compute. So maybe it's not that interesting for quantum gravity context, these models, but it's a toy model, and maybe we can find something more interesting in the future. Okay, thanks.
Thank you very much.